Not analysis.
Curb your enthusiasm.
Okay, so we now address the critical case, and this is what we will do for the rest of today's lecture. So the third case is Ry epsilon is of order epsilon squared. So for y is 1 and 2, and here we have strong coupling. Okay, in this case you have the following system. So of course strong coupling is interesting, but you cannot hope to explicitly solve anything, which is expected, but you can obtain the well-positiveness result. So we have the following system. So minus Laplace u kappa plus dp kappa over dx1 e1 is equal to 2n, and we have the rotation. I'll write it down again. It's not so long, so dv3 over dy2 minus dv2 over dy3. Okay, plus the rotation of y, v1 kappa. Okay, then by y you have the divergence equation. So divergence u kappa u star kappa is equal to 0, and epsilon squared minus alpha Laplace y star kappa v kappa minus beta gradient of y kappa star. So this is the gradient divergence term. Plus 4n v kappa. So this is 2n du3 kappa over dy2 kappa minus du2 kappa e1 plus the rotation of y kappa u1. Okay, so this is system 7. So here we assume that R1 epsilon is alpha epsilon squared, and R2 epsilon is beta epsilon squared, where this is of order 1. Okay, so as I mentioned, since these equations are strongly coupled, you basically need to prove the corresponding well-positiveness result, but we need to assume something more about the solution. So since the equations are strongly coupled, then we cannot hope to solve them explicitly. As in the first two cases. assume that the solution is, I don't know if I mentioned it, in the so-called micropolar Poisson form. So let's assume that the solution has the following form. So U kappa depends on y star kappa, and it's just the first component. So automatically you will have the divergence y is equal to 0, and this v kappa y star kappa. So this is natural to assume when you have this microtation given in this form is in the form of the other two components are non-trivial, but the first is trivial. So okay, and dp kappa over dx1 is a constant. Okay, so this is the so-called, I'll write it down. From the literature, it's called micropolar. So it's just generalization. Let's say solution. Okay. So what you obtain now, you have the following problem. So we now obtain from 7 the following system. So minus Laplace. I think this is the last system that we will write. So Laplace E1 kappa plus dp kappa over dx1 E1 is 2n dv3 kappa over dy2 kappa so this is in V, and then minus alpha Laplace V kappa minus beta gradient of the divergence of V kappa plus 4n. V kappa is 2n rotation u1 kappa in B. And of course you have the boundary conditions that u1 is 0 and V kappa, which is V2, V3 is 0 on the boundary. Okay, so of course these kinds of problems are addressed via the Lax-Milgram theorem. So let's go a bit through that for this case. So of course you consider the following problem. So we consider so the following problem would be find big U kappa, which is U1 kappa v kappa, which is from h01b times h01b squared, such that so b u kappa v kappa is minus dp dx1 kappa with v1, where this is the L2 inner product. So this is for every v kappa v1 z from h01b okay, so you have this. I'll just write it down. So this, as expected, is the inner product of L2 over B. The notes. So the inner product of L2 over B, while this B is of course a bilinear form. Following way, so I'll write it down. B u kappa v kappa so you first of course obtain the you look at the two equations as basically as one. So the gradient of u1 kappa, gradient of v1 kappa b minus the rotation term. So this is the dv3 kappa over dy2 kappa. Kappa b plus the Laplace from the angular momentum equation. So gradient v kappa, gradient z kappa b plus the term that we obtained from the gradient divergence equation. So this is the divergence v kappa z kappa b plus 4n v kappa z kappa b minus 2n rotation of u1 kappa z kappa. Of course, to prove your well-Bose problem, you need to prove that this form is continuous and elliptic. So, coercive, sorry. So, B that is given from H01, B times H01 B squared. R is continuous. Okay, so you can check this. This is an easy exercise. Prove the boundness, and the coercitivity can also be easily checked. I'll just write down what it means. So the coercitivity in a similar fashion can be easily checked. So you have ln b of u kappa is more or equal to c u kappa squared h01 of b okay, where this c is the minimum of 1 minus n alpha. It's bigger than 0, and n is of course mi-r over 2 plus mi-r, it's less than 1. So when you have these two things, it's more or less an easy exercise. So then the Lax-Milgram theorem. Implies that I didn't denote it. Okay, or maybe I did. Okay, anyway, this bu kappa v kappa is minus dp kappa over dx1 kappa v1. So that this has a unique solution. Unique solution, namely that's denoted by this way, so u1 kappa v kappa in h01b okay, which means basically that, so this means that this solution, so u kappa solves our problem 9 weakly. With this pressure being constant. And being equal to 0 on the boundary. Okay, so this is regarding this well-positive result, which is not hard, but I just wanted to maybe remind you. And just a final remark. So then we will continue this paper next time. I think it's better to separate it. So remark 1. Just regarding the pressure and the difference between the first two cases and this one. So since the velocity approximation is not computed in explicit form, so it's not obtained. So you cannot directly recover the pressure, so we are not able to recover the value of the junction pressure we did. In the first two cases. But you can basically obtain it in some explicit way, just claim that it can be obtained. So we can only claim so that it is given implicitly. Via the incompressibility condition. Since this integral over b u1 kappa is different than 0, how do we check that this is true? Well, it's easy. So, yeah, you can denote this by star, for example. If I didn't denote it before, I don't remember. So how do you check that this is different than 0? Well, you can write this from star and the coercitivity. On B, we have the following. So C u kappa in the appropriate norm times h01. So by the coerciveness, you have v u kappa, which is by star equal to minus dp kappa over dx1 kappa, u1 kappa. Okay, so since dp kappa over dx1 kappa is a constant, now if the integral of b u1 kappa would be equal to 0, this would imply that u kappa is equal to 0, which would contradict our system 9, which can be easily checked. So this is just a short note regarding the pressure. Okay, so next time I will talk a bit more about this paper. We will have a similar procedure, but it's good to maybe to let it sink in regarding the matching between the junction and the pipes, where the solution is of micropolar Poisson form. So more next time. Thank you for your attention.